All right. Now we're going to talk a little bit about a conceptual understanding of what's going on, and this is going to set the stage for some of the things that we'll need later on when we look at how we adjust switches. It's also going to explain a little bit with some of what we've seen with equivalent resistance. Now, I mentioned this in one of the previous videos, but I want to talk about this yet again. Path of least resistance, because a lot of people misunderstand this. Path of least resistance. So, what people understand this to mean is that current will always go in whatever the easiest path there is. That's not exactly true, it turns out. And that's why I don't recommend actually using this. What ends up happening is the following. And for that, what I need to do is give you an understanding, at least a conceptual one, of a way to imagine a circuit so that you can actually apply this without having to run through all of the math every single time. Now, I've built a kind of complex circuit here. It looks pretty bad right now because I have a bunch of ammeters built in so that I can measure the current as we get this turned on. But I've got a battery here. We've got it go through an ammeter here, but it's basically just a wire. So battery, and then we have a light bulb here, and then it splits off where we've got 3 other light bulbs. These 2 are in series with one another, but in parallel with this one. So if I were to draw this out, it would look a little something like this. Here's my battery. I've got a resistor, which we will use as representing a light bulb. I've got this here. This is the one light bulb by itself. And we've got these 2 light bulbs here. Now, the biggest thing that is kind of new that I'm too lazy to draw in on a regular basis is I've got a switch right here. And we're going to talk a little bit about this because I want you all to be able to compare this when we start trying to get an understanding of what's going on in the circuit. The thing about it is this. Don't think of electricity as one little thing that's trying to march through. It's the entire circuit is filled with charges. There are negative charges and positive charges here in the battery. There are negative charges and positive charges here in each of the different points. Why? Well, because all of these things are made out of, and we talked about this in class, atoms, where they've got positive charge in the nucleus, and we've got negative charge going around the outside edges, the electrons. Now, in real life, what's actually happening is for an electric current to happen, we have a simplistic way of imagining it is one electron jumping to another atom. They're the ones that can move easily. The only problem is the only way that they can move is if the one in front of them moves. And for that one to move, the one in front of that has to move. Now, this is a gross oversimplification of what's going on, but it still gets across our idea. Now, this is important, and one of the things that I want to tie together, because it's fundamentally a key thing that you want to keep in mind while thinking about this. Because you may be thinking, well, how does anything move at all if for this one to move, the one in front of it has to move, and that one in front of it has to move? Basically, you have to have an opening over there, so something has to be missing some charge. We have to have something that is positively charged. Say a proton by itself. Not that they're made out of hydrogen, but it's simpler to draw it this way. But that's not the case. Everything in our circuits, for the most part, is electrically neutral. So, how can any of these move because the one in front of it has to move? Well, that's why this thing isn't doing anything right now, because I haven't completed the circuit. When I complete the circuit, we can see the light bulbs come on, it starts doing something. None of the charges move until the following. Let me draw this out for you. Here's the idea of a circuit. A circuit isn't just, oh, we've got a battery here and we're going to put some stuff out over here and then the charges are going to run off of the battery onto that. No. In order for anything to happen with these, we need a circuit. And why is that? Well, here's your answer. It's a simplified version of what's happening in real life, but effectively, it's what's going on. In a circuit, the charges are playing musical chairs. The only way that you can move in musical chairs is if the person in front of you moves. This is why you need a circuit. It's kind of like a bunch of people holding hands and everyone takes a step to the left. Everyone moves slightly in this circle. And this is why if you break the circuit, this one can't jump anymore. And because it doesn't move, this one does not move, this one does not move. Nothing can move anymore. This is why we need a closed loop for a circuit. And it has to come back to the battery that it's at, because what's actually happening in a simplistic approach, but very useful analogy, is that they're all playing musical chairs. And the only way that one of them can move is if the one in front of it moves. And the faster that the one in front of it moves, the faster this one can move. All of them have to kind of move together. This is what's happening in a circuit. Now that, first and foremost, is something that we need to understand. It also explains why, if I don't have this in a complete circuit, nothing at all happens. No charges move anywhere. If, however, I complete the circuit, all of these charges can start moving. Now, one of the things that I want to emphasize is this. It's not that charges, when I complete the circuit, instantly start moving out of the battery. They do, but it's not that they're filling a void where there's no charges there. The ones that are coming out of the battery are taking the place of the ones that were here, and those have moved over. They're all leapfrogging their way forward, so to speak. There are charges all throughout this circuit. And one of the things that I want to mention is, as we move forward, I don't want you to think as soon as I complete the circuit, we have charges rushing over here and they get to here first and then over here. That's not how it works. They all actually start moving together at once, at least for our purposes. Now, the reason that that's important is it doesn't matter if I have this light bulb on this side or if I were to redraw it and put it in over here, because no matter where it's at in the circuit, all of the charges have to be moving through this thing at the same time. Now that we've established that, here's what's happening inside a circuit, and most importantly, why we have to have a complete circuit. Let's talk about what these charges are doing. Now, this is kind of in contrast to what I just told you to imagine, but it's my preferred way to imagine a circuit. So a circuit, let's imagine that we have a battery. Okay, so I've got the small end here and then the big end over here. This one's the positive. And I'm going to have a wire that runs over to some component. And then a wire that comes back over to the battery. Okay. It's not completely representative of what real life is, but I found it's one of the easiest ways to imagine what's going on so that you can conceptually get an idea of what a circuit's going to do. What I want you to imagine is this, that the battery has a whole bunch of positive charges on one side and a whole bunch of negative charges on the other side. And the positive charges are repelling one another, pushing them away from one another, and they are being attracted by the negative. Now, this is not true because charges can go through the battery, but I want you to imagine that there's a wall that separates the two of them. So the positive charges are pushed away from each other and are attracted to the negative. So when we give them the opportunity, by completing a circuit, you can imagine that one positive charge is flowing out this way. Now, as we just talked about, what's actually happening is electrons are moving, and they're all moving the opposite way. So one electron jumps here, when the one in front of it jumps in front, in front, in front, in front. We actually had an electron over here that's jumping into the battery, and they're all jumping at the same time. That being said, while that's the much better representation of real life, for our purposes, for right now, you can imagine that we've got positive charges that are trying to get from one side of the battery to the other. Now, the reason that I describe this is the following, because this is one of my favorite ways to take a complex circuit and start to predict what's happening with the different components. The place where you have the most experience with this, at least that I like to draw attention to, is at the end of our assemblies at school. We're all in the gym, and we're all tired of being around one another, and everything's done. We want out of the gym. So this side of the battery, you could imagine, is effectively the gym. And there you are, you're one of the positive charges, surrounded by a bunch of other positive charges, and you all do not want to be near one another anymore. We've spent an entire hour together, we need to get back out into the halls so we can spread out and recharge, and yeah. So, you are just like the positive charges. Now, you're trying to get out of the gym, and the circuit represents getting out of the gym, the different places that you could go. And where you're trying to get is the negative side of the battery, or more accurately, just out of the gym. Now, in our gym, we've got a bunch of different doors. It all depends on where you're at, but we've got some doors. If you're down on the lower level, you have to go up some stairways here, or maybe over here. There's maybe a stairway over here, maybe over here. It all depends. And then we've got kind of the main gym doors back over here. that everyone is trying to get through. And some people are up top, so they have to come down some stairs. It's a big place, and it's kind of a mess. And as you've seen, as you've experienced, it takes a while for people to get out of there. Now, the big idea on this is we've got a bunch of things crammed together, and they're going to go... Let me rephrase that. Let's bring back in the path of least resistance. So here's the thing. Let's say that we're looking at the gym, and we're going to exit the gym, and we've got a big set of doors that are 4 doors that are open. And you've got a bunch of people who are looking to get out of the gym, and they want out of there as quickly as possible. Now, you're going to have a bunch of people go to the 4 doors, and they're going to start going through them, but just like you've seen in real life with our gym, we end up with, well, only so many people can get out at a given time, so we end up with lines that start forming. Now this is 4 doors wide, so it's pretty easy to get through. What if, in addition to these 4 doors, maybe a little ways down the way, I opened up one other door? Now here's where the path of least resistance starts to fall apart, because path of least resistance, the way most people think about it is, oh, I'm going to go the easiest way. But remember, current is not just one thing. It's not one person. It's a bunch of charges. Billions of them trying to move from one place to another. So it's not simply one person looking at the doors going, I'm going to go the easiest one. It's a bunch of people going, what's going to get me out of the gym the fastest? Well, if you've got a line built up here and I open another door, it doesn't matter that this one's harder to get through, that it's a little bit thinner. You're not going to have everybody waiting patiently in line to go through these 4 doors and one door's sitting over there and no one's using it. Someone back here is going to go, well, nuts to this. I'm going to go through that door. And someone else is going to go, oh, this line is 6 people long. That one's only got 2 people. I'm going to come over here. And you're going to end up with what we end up with in the gym. You're going to end up with a line about some length here, a line about some length here. In short, you're going to end up with a lot of people, maybe 4 people per second getting through this door. And you're going to end up with 1 people per second through this door. This is what current is actually doing. It's not one charge that's going, well, I'm going to go the easiest path, and all of it goes the path of least resistance. It's thousands and billions of charges, maybe thousands of people, but billions of charges, and they're not going to all wait patiently in line going, this one has 4 doors. I can fit through that one pretty easily. I'll wait in line for this one and nuts to the 1 door. No, it's going to do exactly what we as people do in real life, pushed, if you will, by our desire to get out of the gym and away from one another as quickly as possible. You're going to go to the 4 people door and the 1 person door in pretty much equal proportion. We're going to end up with 4 times as many people getting through here as we do through there, but we're going to end up with lines that are about the same length. And when a new person comes over, they're going to go, okay, well, I'm going to go to the shortest line, which means they'll start filling in here and here and here. But if that line gets longer, then they'll start filling in over here. And we're going to end up with, while all the people are trying to get out, you're going to end up with about 4 times as many people getting through here as you do here. And it's not going to be that this is the easiest path, it's the least resistance, so everyone goes through this. No, people are going to split up. You're going to have a bunch of people go this way, a few people go this way, and they're going to get out of the gym as fast as they can. Now, this is the other thing that I'd like to bring up on this. So, when we look at something that's in parallel, I mentioned the following. That if we had 2 resistors, one of them is 100 ohms, and one of them, let's go with the other one being 100 ohms. Okay? I told you that their equivalent resistance, REQ, must be less than 100 ohms. Okay, well, let's say that we end up with let's look at this from the gym viewpoint. In fact, I'm going to erase this, and let's do a direct comparison on this. Because here's where the gym relationship actually starts paying off. I've got, each of these paths is a path out of the gym. So I'm stuck in the gym over here. These are my circuits, these are my paths out of the gym, and out of the gym is the other side of the battery, is the way that you can think about this. Well, I've got two paths here. So I've got it coming from the battery, and then it splits off. There's one path here and one path here. That's the equivalent of having one door and an identical door a little ways over. And as we just saw, we're going to end up with a certain number of people going to one door and a certain number of people going to the other door. And for the most part, we're going to get about an equal amount of people through each of them. Well, that makes sense because they're both the same resistance. So our current, half of it's going to go this way and half of it's going to go this way. All right. What if we were to close one of those doors? I'm going to break the circuit and we're going to close this door. We used to have one person getting through here and one person getting through here maybe every second. But if I close this door, this one goes away, and instead of having a total of 1 plus 1, I had 2 people per second. If I close this door, I only end up with 1 person per second. Well, that changes my current, how many people are getting out of the gym, how many charges are able to go through. So here's the idea. If I open this door back up, then I go back to the 2 people per second. I've added a resistor, yes, but because I put it in parallel, it's me opening another door, which allows more people to get out of the gym in a given time, which is useful. What if I were to do, so on that note, that means that having these 2 resistors in parallel let more people through, and the more people that get through, that means our equivalent resistance, the resistance of the whole thing, goes down because more people, more charges are getting through. All right, what if I were to add a third one? I'm going to open another door. In fact, when we get to talking about what changes in circuits, you're going to hear me talking about opening and closing doors because it's my favorite way to imagine this. Let's say I'm going to open up another door here. Let's say that this is a 1,000 ohm resistor. What's that the equivalent of? I've opened up maybe a short door. Maybe it's like a doggy door or something. But if you're staring at a bunch of people in line and you see an option to get out of the gym, I'd expect a number of people are actually going to go through there. Now, it's going to be a lot harder to get through there, which means we might only get something like, it might take one person per maybe 5 seconds to get through there. Might take a little bit longer for you to finagle your way through that harder door. That's effectively what each of these are. And the resistance, 100 ohms and 1,000 ohms, are describing how hard it is for charges to get through that resistor. In other words, how hard it is to get through that door. Well, if we have a doggy door there, it's going to take people a lot longer to get through than if it's a nice, large, comfortable door. And so that's how you can imagine it. It doesn't matter that I've opened a really small door. If people can get through it, they're going to go through it in the effort to not have to wait to get out of the gym. And you're going to end up with a slight increase of your current. We're going to have more people get out. I'd have to do some numbers on this. This is 1 person per second, 1 person per second, and a fifth of a person per second. So you get 2.2 people per second. 2.2 people per second, which is greater than 2 people per second. I open another door. Even if it's really hard to get through, some of those charges are going to squeeze through in their effort to get from one side of the battery to the other, to get out of the gym. Opening the door here is going to actually allow us to have more people go through, and that means your equivalent resistance must go down. That's what leads to my statement about if you have them in parallel, you put another one in parallel, you will lower the equivalent resistance because the equivalent resistance will always be less than any one of the individual resistors. Why? Because you've opened something else up and it allows, even no matter how difficult it is to get through it, some of the charges, some of the people will try and go through it. It may take them a while to get through it, so we may not get a whole lot of current, but it will add an avenue where more people can get through than if you just had the one door. All right. That's what I like to bring up on this because it makes it easiest to work with more complex circuits and predicting what's going to happen when you add resistors, or pathways, I should say, or remove them. Now, the other thing that I'm going to bring up is this. If you have things in series, that's where you end up with, okay, well, if you're on the ground floor of the gym, for instance, and you need to get up out of the gym, you got to go upstairs, which means everybody's going through this set of doors, but you might take a path here, which is the stairway here and the stairway here. If I close down one of those stairways, it's going to slow down how quickly people are getting out of there and lower my current. That's closing a door. However, the more doors you put in front of people, here's series. So parallel is opening doors side by side, opening more doors to get out of the gym. If you put them in series, you basically are increasing more bottlenecks, hard places for people to get through. So we have a door here, and for most people to get to it, they have to go through a section here and here. These are in series, and with these being a choke point, it slows down how quickly people can get through. That's kind of the idea in series. If you put a resistor in series, then the two resistances would then add together, making it harder to get through. You can imagine these having doors where you have to go through, open them up, and close them behind you. The more doors you have to work with, you get slowed down by having to do all of that. However, if you've got them in parallel, the amount of time it takes for you to open and close the door is still small compared to the amount of time you would have been waiting in line. All right. Now, the big thing about this is to get across the idea of what charges are actually doing in the circuit. And the last thing that I'm going to bring up is this. We talked about this at the beginning. All of the charges in the circuit have to move together, so it does not matter if a switch is over here, or if it's over here, or if it's over here, at least in order. It does matter in what branches it activates or turns off, but I can try and show this. It doesn't matter for this light bulb that it is before the break, or if it is after the break. All that matters is that it is still in series with both of these. All right, so let's take a look at this and apply it to the one that I've actually got here and see if we can make some predictions or explain what we see. Okay, maybe I shouldn't have erased that, but that's fine. So here's what we're going to do. I'm going to bring this out, and let's take a look at this circuit that I've made. The circuit diagram is here. Now, right now, I've got my switch set to off. I can remove it completely so that you can see that that is just broken. I'm going to leave it on off. In other words, I've closed this door. I'm going to connect this. Now we've got a circuit, but this is a closed door, and we've got a bunch of people trying to get out of the gym. They come through here, and apparently at this point, we've got about 1 amp going into this light bulb, which is then going over here. Nothing's going this way. You can see I can remove this, and it does not change my circuit at all. So everything's going this way. So the 1 amp, the 1 coulomb per second is going through all of these parts. We can see here, this is about 1 coulomb per second. All of that's going through this light bulb and going through this light bulb and coming out over here. We've got 1 coulomb per second. They're all going like this. Everyone is musical chairs-ing their way around this circuit. Now, the other thing that I'll bring up, and this is common on the AP exam as well, all of these light bulbs should be identical. In fact, you see they're all about the same brightness because if they have the same resistance, I don't know what that resistance is, and they have the same current, we have I squared R equals R power. They all have the same current because everything coming through here has to go through this one, has to go through this one. And since they're identical light bulbs, they all have the same resistance. Since both of these values would be the same, they all have the same power. They're all about the same brightness. So here's what I'm going to do. I'm now that we've got everybody going single file through just this branch out here, because I've broken this one, I'm going to open a door here. So what we've got is basically one doorway and then another doorway after it and then another doorway after it. And what I'm going to do is I'm going to open another doorway here so some people can go this way and some people can go this way. It's going to change how long these lines are and how long it takes to get through each of these. Let's see what happens. Although, real quick, let's predict. I'm going to have these two doors will be completely unchanged, but I'm going to have another door here. So that's going to allow more people who are waiting in line here. Well, some of them go this way and get stuck in line there, but now we've got a new path, so some of them are going to come over here. So what's going to happen to the number of people moving through this door? Well, since we have some moving over here and some getting in this line, then we're going to have that we have more people that can start getting through this. Let's find out. Now, this represents our main door. Let's see what happens to our total current. First, I'm going to flip the switch. Let's see what happens. Each of these bulbs are about the same brightness. And 3, 2, 1. Well, that's an interesting outcome. I'm going to flip this back. This is at the heart of what many of the questions, both in my class and on the AP exam, you're going to run into. All right, this is about 1 amp, a little bit less than 1 amp actually, a little bit less than 1 amp, and a little bit less than 1 amp. This has nothing going through it because I've opened the switch. I'm now going to close the switch, and we see that this one gets brighter, these get dimmer, this one got brighter, and let's see what happened to the current. This is now a little over 1 amp, this is about half an amp, and this is about half an amp, and over here we've got about half an amp. So what we used to have was 1 amp going through the first resistor, then going through the second resistor, then going through the third resistor, and coming back over here, 1 amp in each of them. They all got the same current, they had the same resistance, and thus, once again, they're all the same power or brightness. But when I flip this switch, I changed things out. I've opened another path which allows more people to get through here. First off, people are going through this door, which means they're actually, we're now getting some charges moving through this light bulb, bringing it energy, and it turns on. Okay, and we talked about this. We now have more charges, more people getting through this door, because some of them go over here and some of them go over here, and so we end up with more current. Before I said it was a little under 1 amp, we're just under 1.5 amps now, and all of it is going through this door. So we have a high current right there. And then it splits off because some of them are going this way and some of them are going this way. Now, keep in mind with each of these doors, if you have to open them and close them behind you, it's going to take more time with these 2 doors here than it would this one door that will get you over to the other battery. So this line is going to be moving a little bit faster. So what I could say is we could call this IA, this one IB, and then IC for the currents. The current that's going through the main one here, the current that's going through this branch, and the current that's going through this branch. IA is going to be the biggest. Why? Well, because it's our total current. Whatever's going through here and here is coming from this point, which means all of the current is going through this one. So that's greater than the others. We can see, it can be kind of hard to tell with my video, I'd imagine, but this one's next brightest, and these 2 are pretty dim. Well, we can conclude that our current in B, because they're all identical resistances, the brighter one will be the one with more current. We end up with this relationship, which also makes sense because it's twice as easy to get through here than it is over here. In fact, let's see. So if I read this closely, this looks almost 1.5 amp. This is about a little less than 0.5. Same thing on this one. And this one over here is probably about 0.7 amp. So this is probably more like 0.12. That being said, if we apply our knowledge of, hey, these resistances should all be the same, we should have twice as many charges going through this side as we do over here. So I could go through and do some math on that, but I want to show you what we can conclude. Sorry about that, my video cut out. Just a quick recap of what we're doing to finish this up. I have a circuit going here. I want to make certain that we've got an understanding and how you can apply this gym and doors idea on what we're looking at. So right now, I've got the switch open, which means no current is flowing through this branch. So basically what we've got are 3 doors. I'm going to erase all of this. We're going to keep in mind that each of these bulbs are identical, or at least as close as we can get them, which means their brightness is going to tell us how much current effectively they're getting through there. So the power, the brightness of the bulb is equal to I squared times R. If they all have the same resistance, then the one that has the greatest current will be the brightest bulb, and the one that has the lowest current will be the dimmest. Okay. Now all 3 of these are about the same brightness. The reason why is we've got 3 doors, and as each person goes through them, they have to open the door and close it behind them, which will slow them down a little bit, which is a little silly, but I want to try and get across the idea that it's difficult to go through these resistors, and since we're talking about doors, the thing that's going to slow you down some is if you have to open the door and close it behind you. So, a little silly, but we'll go with that. So we've got 3 doors, and the amount of people getting through this first door, well, all of them go to the second door and into the third, so they all have the same number of people per second. In other words, the same current. Once again, current is like counting cars per second or people per second, but in reality, for actual current, is charges per second. Great. Okay, so these all have the same current. We've got a little bit less than 1 amp, a little bit less than 1 amp, a little bit less than 1 amp. So all of them have the same current going through. Here's what I'm going to do. I'm going to open a door here. And what that does is it allows people to start going this way. So everyone's still going through this first door, but we end up with a line forming back over here and a line forming over here pretty much instantly. Again, the charges are already there. We're just letting them kind of move. So what we end up with is, well, this has 2 doors, so you're going to be slowed down by each of these. This one has only 1 door, so we're going to have twice as many people per second coming through this as, let's say that this is 1 person per second. Now, that means that we've got people kind of flying through this door, getting to stand in line over here, is the way you can think about it. And so we're increasing, since all of the people have to go through here, and we've opened another door, allowing people the lines to move a bit faster, we end up with 3 people per second. Now, it used to be 1 person per second, mainly because, well, we had other doors in the way. You could have a big, wide open door, something that could accommodate 8 people, but if it's completely filled with people waiting to get through a small bottleneck in front of them, it doesn't matter. You're still going to have 1 person come up and kind of stand there for a while. So you can have a big open space. Like there are times where we're trying to move through the larger hallways in school, and you can't move very fast because there are people in front of you. It's the same idea as the musical chairs. For anything to move, the thing in front of it also has to move. And each of these doors are going to slow that down. So in this case, when I open this door, it allows people to start funneling off here. This line is about the same because or not about the same, I should be careful. This line gets affected because of us changing the circuit. Whenever we change one thing, we change everything about it. So I'd have to change some of the numbers. So putting that in perspective, if I open this switch, what we saw before with the 3 doors, close this door, we have a little bit less than 1 amp going through each of them. But now when I open this door, I change the resistance of the circuit. I change how many people can get out of the gym in a given second. And as a result of that, everything will shift. It affects all of my lines as people start going this way versus that way. So my camera's acting real weird right now, but that's okay. Just finishing up here. As we change the different parts of the circuit, it ends up changing everything. So just a quick overview. Once again, the switch is open here. Everything has to go through each of these, and they end up the same brightness. When I close this switch, it's like opening another door, allowing multiple paths. That lets more people out of the gym, and all of them go through this, so we get a higher current, and this one gets brighter. And these get dimmer. They used to be bright. Now they've gotten dim because while we have more people getting out, not all of them have to go through this branch anymore, so this ends up having fewer people go through. This ends up with more people, more charges, I should say, going through, and so it ends up getting brighter. And how the current will break itself up is going to be in relationship to how quickly it can get through these, the total resistance of them. Just like the doors. More obstacles, that line is going to move slower. All right. One of the last things that I want to bring up on this, I've mentioned it a couple of times, but I know that it's an issue that I've run into with students on quite a few different circumstances. The order of this does not matter. Let's see. Now, my ammeters won't work quite right if I reverse this, so we may not be able to read what the ammeters have, but I'm going to flip the batteries. In other words, I'm making this one go to the opposite side over here. All right, so in doing so, let's see. Now my ammeters probably aren't going to register properly because they're direction sensitive. Here we go. Ah! Sorry about that. Now I've reversed my batteries, putting this in the exact opposite direction. We still see that this one's the brightest because the switch is closed. In fact, these come up and they look pretty much exactly the same. Let me flip my switch here and it goes back to exactly what we saw before. It doesn't matter if this door is in front of the others or at the end. The order on this doesn't matter. It's just how we've got this set up. And the reason the order doesn't matter is because all of the charges are all moving at the same time. It's not just one running out here and, oh, I got through this door, so I'm good. I go somewhere else. That's kind of the big thing about this path of least resistance. It makes people think that there's only one thing trying to move through. There are billions upon billions of charges, so the better way to think about it is a large group of people trying to get through a tight area.